Okay, so thanks for coming back. We are about to start this afternoon. We will start with the lecture from Professor João. I'm really happy to see you again at KAUST. It's your second time here, I think.
Second time, yeah.
Yeah, it's really a pleasure to welcome you. And I'm really looking forward to your talk about biomethane in industry. Biomethane, okay, it's not a carbon-free fuel, but we already had some talks where they explain how this type of fuel could help us in the transition to net zero carbon. So when you're ready, you can start.
Thank you. I'm going to talk about some of my experience with biomethane and also some experience with mixes of gases or mixtures of gases, few gas. So the biomethane is also called renewable natural gas, or RNG, is methane derived from biomass. And I have here a sketch. There are two paths to obtain biomethane. One is through biogas upgrading, and the other one is using gasification. And most of the biomethane that we obtain today is 90% from the first route, or the first road, as they call it here. So the concentration of methane in biomethane should be more than 97% by volume. And in Brazil, it is required 95% by the National Agency of Petroleum, Gas and Biofuels. The contents of my presentation, I'm going to talk about fuel gas interchangeability. How many of you are aware of the VOB index? Heard the VOB index? Okay. So it's good that I explain. Okay. Biomethane production and distribution, use of in industrial equipment, glass melting furnaces, ceramic tile furnaces, fluid ice bed, sand dryers. I'm going to talk about some economic aspects and conclusion. So interchangeability. You know, if you have a stove in your home and you're burning LPG, your burner is designed to burn LPG. So suppose that now you want to burn natural gas in the same burner. It's not possible. You have to do something to the burner, because if you put natural gas in a burner designed to burn LPG or liquefied petroleum gas, you're going to have a blowout of the flame. On the other way, if you have a burner which is designed to burn natural gas and you burn LPG, the flame will become yellow and it will make the pan very dirty with carbon residues. So what do you want when you want to, instead of changing the burner, in here it's easy, you know, because it's a simple burner, but it's very complicated in terms of doing some design, because it is partially premixed, okay? But what do you want? You want to put a fuel that does the same job. You don't want to change all the settings and all. Suppose in here we have only one burner. It's easy. You have parts to make the change from LPG to natural gas. You can buy them easily. But suppose that you have an industrial furnace with hundreds, sometimes 10, 12, 10, 20, 50 burners there. So you don't want to change the burner. So what you do, you put gas, okay? So for example, if you have a furnace which is designed to burn natural gas and you want to burn LPG in there, don't put the LPG. You mix LPG with something so that it becomes similar to the natural gas. And this is the VOB index, okay? The VOB index is the most important parameter for defining the interchangeability. It's an indication of whether a burner can be operated with an alternative fuel without requiring adjustments or physical changes. So you don't want, it's like you have a car, you want to burn another fuel, you don't want to buy another car. You want to prepare the fuel to burn in there. So the VOB index was developed in 1926, 27. I leave all the references on the bottom of the slides. The VOB index is, it arises from the thermal energy in kilojoule per second is the calorific value of the gas. I'll discuss some about it. Sometimes it's not the calorific value of the gas. It is the heat or that you need to have your product at the required temperature, okay? And, but anyway, let's accept that. Calorific value of the gas times the volume flow rate of the gas. So it's kilojoules per normal cubic meter multiplied by normal cubic meters per second. So the formula how do I get the in here? Go in there. Okay. So the formula is here. You have a calorific value of the gas, and then this is the area, the orifice discharge coefficient. You can think about an orifice, and delta P over rho, square root of this, it comes from the Bernoulli equation, okay? So, Q is the rate of thermal energy that you want to keep, okay? So this is one thing that you want. The calorific value of the gas can be the lower or the higher calorific. I'll talk about it in just a moment. So the formula can be written as if you divide the density by the density of the air, you have here the relative density of the fuel, okay, or the relative to air, or density of fuel relative to air. So VOB defined his index as delta H, or the calorific value of the gas, divided by the relative density, so that you have just putting there is the index, the VOB index times the area times the discharge coefficient multiplies the square root of the manometric pressure. So in here, there are two types of VOB numbers. One is called the high. Instead of putting here, you put here the high heating value, and the low is the lower heating value that goes in here. I prefer to work with the low heating value. It doesn't matter which one you use, because you're going to compare, okay? So if two fuels have identical VOB index, then for given pressure, you see given pressure here, okay? And valve settings, this is most important. The energy output will be also identical. And one of the criteria for interchangeability of two gases is that the index are approximately equal within the range of plus or minus 5%. So to achieve an appropriate VOB index, gas mixtures are used for substitution. Okay, so if you want to burn LPG instead of natural gas, it has to be mixed with something. Okay, a mixture of LPG and air is called, at least in Brazil, it's called propane air. Propane air. I don't know if it is the same. Air propanado.
Not sure we have here something similar that we are burning.
We had a crisis in Brazil in 2008 and 2009, and industries were trying to get an alternative for burning natural gas. So we did some study on that. Just calculate the VOB number for natural gas, then you make a mixture and make it with the same VOB number. There is also a modified VOB index, or VOB number, that takes into account the temperature of the fuel. It is the same thing, except that there is a temperature in there. Okay, you think, well, I have a burner here and I want the same energy output. Why don't I just increase the delta P? Okay, you can do it if you have one burner. But if you have, this is a slab reheating furnace, okay, from the national CSN, is a very large steelmaking company there in Brazil. This furnace is about 30 meters long, and it gives slabs at the rate of 180 tons per hour. So you have, it's, you know, if you're not rigorous, you can say that it is a countercurrent heat exchanger. The hot gases go this way, and the slabs go this way, okay? And each of the zones, each one of the zones, they have their own settings, their own burners. So if you want to increase the delta P, or the pressure difference, if you increase because you put another fluid in there, another fuel in there, then you don't distribute it equally. Then it becomes a mess. Also, when you have the same VOB number, you have characteristics like flame length, the same, or more or less the same. The air flow rate is the same. So the VOB number is the most important parameter. And what you want in a furnace like this is the product. Okay? You have to have this slab at 1,200 degrees Celsius at the rate of 180 tons per hour. This slab, the weight of it is about 20 to 22 tons. There are other indices. Okay, the Weaver developed a method based on 6 indices to measure the degree of interchangeability between gases. And this is in a Brazilian book, but you can find it in other books. The first one is the requirement of heat input. This is the VOB index. Then you have primary aeration for premixed or partially premixed burners. Flame blowout is very important. I will show you one industrial application in which you cannot change the gas. You have to prevent flame flashback. So there is another index. Yellow tips, when the burner is partially premixed, you don't want it, so there is an index for that. Incomplete combustion. It gives you a degree of how much CO you're going to have in the same settings. I'm going to talk about some steel production gases, okay? You have in the steel manufacturing or steel factories, you have three types of gases. One is the coke oven gas that comes from the coke oven battery. The coke is something that you have to feed to the blast furnace, okay? A residual gas from the blast furnace is called the blast furnace gas, is BFG. And the composition is, I took it from a site here, but the composition is not 20% of CH4. It's about 20% of CO. And it is a very low calorific value gas, but it is energy. So why don't use it? And there is another one, it is the converter gas. It's called LGG. LGG, because it was first derived or first studied in Austria, in the cities of Linz and Donowitz. And this comes from the converter LGG, and also it's called BOF, Blast Oxygen Furnace Gas, okay? And it has, in Brazil, we have this about 70% of CO. It's a very dangerous gas, very dangerous. Now, 70% of CO, there was an accident one day in the CSN, Companhia Siderúrgica Nacional. Still making, I think. Okay. And there was a leak of this converter gas. It didn't kill anybody, but it was a trouble. You know, if you breathe an air with 4,000 ppm of carbon monoxide, it is lethal. 70% is a lot. Of course, it gets diluted. And I have in here the volumetric composition of these gases, okay? Our interest when we're talking about biomethane is the substitution of natural gas. And I put others in here, because sometimes they have to be substituted, okay? Either because the production is cut, either because they have some problems, either because they have to clean the line, like that. So this is another project or another problem that we got involved in. Is coke oven gas, as you see here. Coke oven gas has about 60% of hydrogen. And this amount of hydrogen makes it a fuel that anchors in the burner. It becomes stable because of the amount of hydrogen. You saw yesterday or the day before yesterday that hydrogen has a very high velocity, flame velocity. So it's easy to anchor any flame with hydrogen. We had, one of our experiments, we had a flame of, free flame of methane, and we used only 3% of hydrogen. And so in this is heavy plate heat treatment of Usiminas. Usiminas in the state of Minas Gerais. And it's a very special type of furnace because the burner is not inside directly in the furnace. It goes inside the radiant tubes because the treatments they put in these special slabs does not support oxygen atmosphere. So what do you have there? You have 212 tubes, U-tubes, And about a quarter of them on top, a quarter down, on the other side the same. Have half in one side and half in the other side. They have what they call transmission side and free side. The furnace looks like the one in the right, okay? And they were burning coke oven gas, and somehow they wanted to change it for a mixture of LPG plus air or natural gas plus air with the same VOB number. What happens? You can make this mixture, but it's not gonna hold in the burn. A problem with when the flame goes out, you see these are the U-tubes that go inside the furnace here. Here's the burner, has a swirler, and this is the damaged tube. So what happens? When they open the furnace for maintenance, about 25 to 30 tubes are damaged. You know what happens because the coke oven gas is a dirty gas, and then it makes the diameter for the flow smaller as it is depositing there. So what happens is that the flow gets high velocity, and sometimes the flame detaches from the burner. Then it travels through the U-tube, and the furnace is hot. Then you ignite the whole mixture inside the tube, and you have this kind of problem. So, and when it's impossible to change it from this without doing anything to the burner, okay? You cannot do it. So other parameters for interchangeability are flame length, flame emissivity, furnace atmosphere. You can put another gas in there and ruin the furnace atmosphere. NOx emissions, flue gas dew point. And in here I have an example where the flame length is important. Okay. You have, for example, a sintering machine. Sinter is one of the materials that go into the blast furnace. And besides agglomerating the mineral or it also contains some other materials that are necessary for like some carbonates. And it has about 5%. The sinter is mineral with 5% of coke or a very high carbon content coal, okay? So it has about 5%, you have to ignite it. And the burners are burning from top to down. You can see the flames in here, okay? And ignition requires some energy, and this energy has to be conserved. When you change the gas, you have to provide the same amount of energy. And also the flame cannot spread over the mixture. Cannot spread, and also cannot be so very far from the mixture. It has to be almost touching the mixture so that it ignites. And this, so you have to take care of the flame length in this case. Usually you can have controls. In here, there are, I think, 10 to 12 burners. You can just adjust the flows. It's not a really problem, a real problem. The biggest problem of this sintering machine, you see, there is this thing. Oh, this goes this way, okay? And you have a combustion wave in here, smoldering combustion wave, okay? and you have the sinter, what they call sinter. And in this case, you have particles of carbon and air passing. Where the particles, in the place where the particles are, you have rich combustion. And outside of the particles, you have lean combustion. And sometimes you have an explosive mixture that burns in the electrostatic precipitation. Have to be very careful, okay? People are studying now how to change this coal by charcoal, which is a biomass, okay? But what it does, the charcoal has more volatiles, and it opens this waving here. It opens like this. Then the sinter has no, the quality of the sinter goes down. Okay, now we start with biomethane. I told you about interchangeability. If you have a biogas, okay, and this biogas usually has from 40 to 60% of methane. In here, they're saying 65% is too much. Because this, maybe this is biogas in Germany. But the Brazil, no. Brazil, it's 6 to 40, 40 to 60. So methane goes from 40 to 60, and the CO2 goes from 60 to 40. So you have a process, have many processes to extract the biomethane, and the ratio is about 400 normal cubic meters per hour produces 260 cubic meters per hour of almost pure methane. It is, it is just a measure of how much CO2 you have in the biogas. And then you have a residual gas with a lot of CO2. And when you take the biogas from a landfill and you produce a biomethane, or you either burn the biogas, doing a favor to the ambient. Okay? Because biogas is supposed to account for 14 to 15% biogas from landfills of the greenhouse gases because of the CH4. So you have a carbon credit just for doing this. Upgrading, biogas upgrading. Upgrading can be via carbon dioxide removal or carbon dioxide utilization. And there are several types of technologies, and all of them are described in this paper here, in 2019. It's a very nice one because for each technology, it presents a table like this. You can easily see. I just took one from there, membrane separation technology, which is used in the case of the biomethane that we have near our home in Brazil. In Brazil, we have today 4 plants authorized by ANP. In São Paulo, in Seropédica, which takes the municipal waste from Rio de Janeiro, about 10,000 tons per day. Okay, if you think about a population, you can estimate how much waste comes from them. It's about 1 to 1.2 kilograms per person. São Pedro de Aldeia, also in state of Rio de Janeiro, and Caucaia in the state of Ceará. Caucaia is, state of Ceará is there on top. Here you have São Pedro da Aldeia, Seropédica, and São Paulo. So the one that's producing more today is the one in Seropédica. It's about 200 kilometers from our university. In here you have also other plants, but they're not yet authorized by ANP. They are just starting development, okay? In there in Brazil, we don't have a network for biomethane. It's delivered by trucks. And the trucks are moved by biomethane. Okay? And production and distribution, this figure I got from Gas Verde, which is the one that upgrades biogas in Rio de Janeiro. And Gas Verde means green gas. Gas is gas, okay? So you have the waste is sent to landfills. So you have big trucks in Brazil that take the waste around the city and take it to landfills. Bacteria digest organic material and produce CH4 and CO2. And system captures biogas and prevents the release of harmful gases into the atmosphere. And the biogas is purified. Then you have one of the processes that I outlined before. The biogas is purified to convert into biomethane as required by the regulatory authority. And biomethane is distributed to companies, and companies that use biomethane, this is their advertising, okay? That use biomethane, avoid new emissions and protect the environment. So how is it done in the industry? So you have the trucks. If you enter in the site of Gas Verde, you can see trucks there. You have a receiving table. You have a long storage for gases, okay? You have a decompression station and consumption by the industrial equipment. Usually you mix it to the natural gas. Now we start the effects on industrial equipment. So the first one that we're going to see is glass melting furnaces. It is a very high temperature furnace. It works at 1,500 degrees, more or less, with a 10% of excess of air. Air preheating is at 1,000 degrees. Do you know? This is an easy question, I think. Everybody knows. Why the industry preheats the air? You know, when you preheat the air, you know, for example, if you have a furnace at 1,500 degrees, okay, the process is required, or the process requires 1,500 degrees. So the combustion products leave the furnace at approximately the same temperature. So it has heat, it has energy on it. So what do? You exchange heat between the combustion products and the air so that the air enters heated. When the air enters heated, what happens? You don't need to put heat from the fuel. So the rule of thumb is that at each 100 degrees that you put into your air is 4% of economy. 4% of economy. So if you have an air that comes to at 20 degrees, for example, you heat it up to 600 degrees. It's more or less 6 times 4. 4%. This glass melting furnace, or this glass melting company that we're thinking about here, spends more than $4 million per month. So a glass melting furnace, it works like this. It alternates the flow of the combustion products in the air, a valve that is changed every 20 minutes. It is a question, why 20 minutes and not 30 minutes? This is in all glass furnaces of this type. And you have an arrangement of regenerative blocks. What it does, when the hot combustion products pass through these blocks, they heat up. And then after some time, you change in the air, goes and gets heated at the same time that the blocks on the other side are heated, okay? So this company is a Japanese company, Brazil, and they started to worry about biofuels. Okay, so they wanted to know how they could change to biofuel, and we did a work for them in biomethane, hydrogen, because and also for ethyl alcohol, but just giving you the work in biomethane. So this is taken from their site. It's called AGC, Asahi Glass Company. Is working to optimize the ecological footprint by reducing the fossil energy consumption of its production activities. So it's consuming today about 6 million cubic meters per month. And when I say cubic meters, does anybody know the difference between a normal cubic meter and a cubic meter? Okay, you know, but you don't count. You know, when you think about volume means nothing if you don't know the pressure and the temperature. Okay, so a cubic meter usually in Brazil is at 20 degrees Celsius. And when you say normal cubic meter, it doesn't mean that it is 0 Celsius and or 273 Kelvin, but it doesn't mean that the gas is at 0 Kelvin. It means that you just converted the cubic meter to 0 centigrades, not 0 Kelvin, 273. Imagine a gas at 0 Kelvin. And the cost of this natural gas in Brazil is more than $4 million per month. You have, they have 2 furnaces. You can see 2 chimneys here. It's very close to us. I think Diana saw them when she went there, on the side of the road. And what is the criterion for interchangeability between natural gas and biomethane? So what did we do? We asked HGC to give us compositions of the natural gas for 90 days. And we also asked the guys in Gas Verde, the company Gas Verde, to give us biomethane composition. And as I said, Gas Verde is a company based in Seropédica, state of Rio de Janeiro. It's about 60 kilometers from Rio de Janeiro, which upgrades biogas produced by the landfill that receives 10,000 tons per day of municipal waste from the city. Can you imagine what 10,000 tons per day of municipal waste is? So it's funny that if you plot the air-to-fuel ratio for stoichiometric air-to-fuel ratio that people there call ratio. Ratio, for example, the ratio for natural gas is around 10. Okay? It is a straight line. Funny, it is a straight line, but you can do it with more simple fuels, hydrocarbon fuels, and it does like that. And I also had, besides this 180 data, I had from Ceará in 2018, northeast of Brazil, it's also the same. Okay? So we're going to use that to see what happens. On the other hand, the VOB index for natural gas and biomethane, they are out of the 5% range. So you cannot burn in the same equipment biomethane in place of natural gas. You see, the natural gas itself here, the variation is within 5%. Okay? But if you just exchange it to biomethane, problems. Okay? So we have a spreadsheet. I developed a spreadsheet that takes care of the mixture of 5 gases and calculates air-to-fuel ratio, calculates all the parameters, the lower heating value. It's available to you if you want. Simple, of course, but it's very handy. I would say it's very handy because the ArcelorMittal in Tubarão, it's near Vitória. You know, Brazil, Vitória is about 500 kilometers east of Rio de Janeiro. The control of their reheating furnace is based on that spreadsheet. It's not the same spreadsheet, but it has the same looks I gave them. So it's based on the spreadsheet, the Excel spreadsheet. So natural gas and biomethane. So we computed with this spreadsheet a mix that takes the VOB number to 95% of the VOB number of here. Okay, the mix is a mix with 70% of biomethane. So it's 70% of biomethane. You have a VOB number which is adequate. Another thing is that I think it is very nice too is that the stoichiometric coefficient or the normalized stoichiometric coefficient is excess of air is the same curve for the 3 of them, the natural gas, the biomethane, and the mix. Mix is the one with 95% of the VOB number. So what do you have? Temperature of the furnace is 1500 degrees Celsius. It operates at 10% of excess of air, so the normalized excess of air is 1.10. The air temperature is 1000 degrees Celsius, and the mix is almost 70%, and the VOB number of the mix is 0.95% of the natural gas. So here is the curve of the specific enthalpy with the temperature. And what you want from your fuel is this amount. This comes from 1000 degrees and goes to this temperature. This is the adiabatic temperature. What happens in there is that if the furnace is taking something at 1,500 degrees, this amount of energy from the fuel that stays in there. So why do I like to use this one? In this case, you don't have a problem. But in other cases, for example, if you had a mix that had a small temperature, okay, the amount of fuel that replaces the other one is not the ratio between the calorific values. So what do you do here? The LHV of natural gas that we have here in this table, divided by the lower heating value of the mix, is 39.66 over 3588 is 1.1053. And in this case, what we require from one fuel to the other is 560 to 508, which gives 1.1025, which is very close to 1.1053. The other way is also the LHV of natural gas over the LHV of the mixture is approximately the ratio. Remember, it's a straight line, okay? Then it comes to this slide that gave me the most problem, okay? It's easy, but it's difficult, okay? So what happens in an industrial furnace? Usually the air is kept constant, the airflow rate is kept constant. And as the air has a volume flow much higher than the fuel, any variation that you do in the fuel changes the temperature a lot, but doesn't change the volume flux. Doesn't change, but for example, if you have, I'll show you here, doesn't change almost nothing, because if you change the volume flux of or the volume rate of the combustion products, you change the residence time. If you change the residence time, you change conditions for heat transfer, it becomes a mess. So if the air is constant, what do you do here? You put the stoichiometric coefficient for the natural gas, the normalized, V of the air, so this V here is the volume flow rate of air, volume flow rate of natural gas over the ratio, okay? Because then if I multiply here, okay, I get the same, okay? Same in here. So that if the stoichiometric coefficient is equal to this, it means that V of the mix is multiplied by LHV of the mix is the V of natural gas, or volume flow rate of natural gas, times the LHV of natural gas. Then the heat input would be the same. And so the Volb index would remain unchanged, and the normalized air excess would remain constant. But this is what doesn't happen. We have the Volb number is, the Volb index is 95% of the original Volb index. So what does it mean? That the energy input, when you just change from the natural gas to the mixture, the volume flow rate of the mixture is 95% of the value it should have, because the lower heating value, the LHV of the mix, doesn't change, okay? And therefore, the normalized air excess just after substitution is 1 over 0.95 of its original value, That is, instead of being 1.10, it goes to 1.158. Temperature will be lower than the required because the heat input is 95% of its original value. So what the control does? The control is based on temperature. It's more fuel. Okay? The furnace controls will bring the temperature to its required value by increasing delta P, and in consequence, the volume flow rate of the mixture. The normalized R excess will return to its original value, 1.10, and the furnace atmosphere will return to the original in terms of oxygen concentration because of this graph. Okay? Because of this, you see. So it is nice. The only thing is that if the VOB number is too low, distribution is not adequate. Then ceramic tile furnaces. We also did some work with this kind of industry in Brazil. You see here is one in Porto Ferreira, which is in the interior of the state of São Paulo. This furnace is about 100 meters long. You see the ground is dirty. This air tubing here does not exist. Okay? And you see how many, the yellow is a natural gas. Mass, which is here, I mean, the quantity of burners that you have. And they make these very nice tiles. Okay? Very nice ones. It's like a fancy restaurant that has a messy kitchen and gives you a plate with a small leaf on top of it. Charges you a fortune. And it is, okay, so what happens if you do the substitution in there? These tiles, they have something which is very important. The oxygen atmosphere, you see they have a bunch of burners, and they have a temperature profile that I'm not showing here. But they have an oxygen profile, oxygen concentration profile that cannot go below 4%. Cannot go below 4%. And for economy, it is advised that you should be as close as possible, okay, to the theoretical value that is recommended by this publication here. So we did the work in there with the air. I told them, the students, not 2 students went there. I told them that if we go to the air valve, which they keep constant, and we close it, okay? What happens when you close the air and maintain the fuel rate? Temperature goes up. So what does the control do? Takes the fuel out. Okay? So when you take the fuel out, or you lower the fuel rate with another set of air, then burning less fuel. So it's economic. Okay? So it was the way of approaching this red curve. You see the red curve was measured in 1 day in 2019. And they worked in several burners, closing the air, and got this curve down here. And this created about 10% of economy. But there is a problem. What's the problem? Let's go back to the nice pictures in here. You see, the one on the right, on the left here, is a small, what you call tile for the floor. It's small, 25 by 25. No, it's 25 centimeters. Yeah, and the other one is 70 by 70. This one is 25 by 104. So what happens is that the heat requirement changes. So it's almost impossible to have an economic furnace if you don't have this type of control that the students did in there. Automatic for each set of tiles that you're burning, of tiles that you're fabricating. You see, this is very nice. Plate with a leaf. So it is the same. The temperature there, preheating of the air, was 200 degrees Celsius, okay? And the temperature of the furnace was 1200 degrees centigrades. It is required for the tiles, okay? And it is the same, okay? The same procedure for the glass, and for a mixture of biomethane and natural gas with 95% of the VUB number, controls do the same. Okay? First, when you change, the temperature goes down, and then the control injects more fuel. And I did here, in the case of this furnace, or tile furnace, this 1.212 is the one that gave about 4% of oxygen requirement, the least that the furnace can have. You know, because if you have less than 4%, it interacts with the product and makes bubbles in the product. You see, if you keep the air constant, okay, the fuel, what do you do? If you, this one you get from the spreadsheet. For 1 unit of fuel, in here 1 unit of fuel. This is for the mix. You require 11.70 for the air, and you have 12.73 for the products. But if you want to make this 11.7, 12.91, you multiply everything by 1291 divided by 11.7. So you increase the fuel, okay? You have the same excess of air. The products go to 1405 instead of 14, okay? And the residence time, this is 1 unit, okay? Decays from 1.000 to 0.997. So it's perfectly compatible. Also in here you see for 1.212, we get percentages of CO2 and H2O. They are more or less the same. So I assume, I didn't do it, but I assume here that at the same temperature, the MCV2B. This O2 here, you're asking why is not 4%? Because the 4% requirement is on dry basis. Do you know the concentration in dry bases? I think they do. Do? Okay. When you measure, most of the instruments that measure concentration of gases, they don't accept water. So you have to dry your sample. Then mostly what you have when you have a composition is this one is a fluidized bed sand dryer. This is also nice. You see, it's a low temperature device. You have what's required is hot gas at more or less 500 degrees on the distributor here. Okay, so it's a very high excess of air device. Okay, and then you have velocity here, and it fluidizes the sand, and the sand comes wet and goes down dry. So what do you have here? What's the requirement? Your product is the sand. Your product is the sand, okay? What you require when you exchange from one fuel to the other fuel? You require the same flow rate and the same temperature, which is easy now because you have only one burner. You have only one burner, and the control does that too, okay? And in this case, okay, we have, you see, for 500 degrees, the normalized air-to-fuel ratio for natural gas is 565. Okay, and the temperature is 500 degrees. I didn't tell you how I do the curve with temperature is with an equilibrium program. My spreadsheet also has a procedure to do it with the equilibrium program. For biomethane, it's another normalized air-to-fuel ratio, okay? And the flue-gas fuel ratio is 5306. So what do I need? What do I see here? 60.30 cubic normal cubic meters of air produce 61.38 cubic meters of flue gas at 500 degrees when NG is burned. The same, okay? 60.3 normal cubic meters of air produce 6.30 divided by 52.06 times 5306. Same thing as we did before, okay? Is 6146 normal cubic meters of flue gas at the same temperature burning pure biomethane. At a constant airflow rate, the flue gas therefore increases only by 0.13%. Okay, so natural gas and pure biomethane are completely compatible when given the low temperature required by the process. You can just decrease a little bit of the air if you want to kill that 0.13%. Now we're going to talk about the economic aspects. The prices in February 2023 in Brazil. Biomethane was 0.831 USD by normal cubic meter, transforming this to cubic meter at 20 degrees. So what do? You just multiply it by 273 divided by 293. 273 is 0 degrees Celsius, and it's 20 degrees Celsius. And 0.774 USD per cubic meter supplied by trucks. And they could only supply 10,000 cubic meters per day. You know, one of the problems that we have with biomethane in Brazil and maybe in Europe too is that supply doesn't meet the needs of the natural gas consumption. So the natural gas for consumers who use more than 2 million cubic meters per month is 0.76 USD per normal cubic meter. So it's 0.708 USD per cubic meter. So what happens there? The cubic meter of the biomethane is higher than the cubic meter of natural gas. But then the biomethane has a lower low heating value. Okay, so you need more. So this price is even more expensive, you know. I show you here AGC for the study where it's located, the city of Rio de Janeiro, the city of São Paulo. It's 200 kilometers, so that was the price. So the average low heat values of natural gas and biomethane, we put them before, and the spreadsheet calculates it. If you want the spreadsheet, just send me an email and I'll give it to you. Okay, 39.66 and 34.25 megajoules per normal cubic meter, respectively. So if you offer 10,000 cubic meters a day of biomethane, you're going to replace 8,636 cubic meters a day. There is an NG here that I have to take out. Cubic meters per day of natural gas. Okay, so at a cost of 7,740 USD per day for biomethane versus 6,114 USD per day of natural gas, this equates to a cost increase of $1,626 per day per 10,000 cubic per day. So in this case, carbon credits are excluded because in Brazil, these credits belong to the landfill that supplies the biogas for upgrading. Well, this is what happens there, okay? Because it's considered that the landfill is taking the biogas from the atmosphere. But it does, it helps on the carbon footprint of the company. Now, economic aspects in Europe. I searched for what is happening in Europe. The price of biomethane in Europe today is 30% less expensive than natural gas. So if anybody here questions that, please raise the hand, okay? Current cost of biomethane is 55 euros per megawatt hour versus 8 euros per megawatt hour of natural gas. These equate to, did some algebra here, 0.4875 euro per cubic meter for biomethane and to 0.8212 euro per cubic meter for and I use the conversion rate from euro to dollar. It's about 8% more expensive. So 10 cubic meters per day of biomethane. We're doing this considering 10,000 cubic meters per day of biomethane would cost 4,875 euros per day against 8,636 cubic meters per day of natural gas. That corresponds to 7,091 euros per day. So there is savings in the case of Europe because in Brazil, the cost increases. Okay, so what happened in Europe? Okay, before the crisis, you can guess what the crisis is. Crisis Russia, no? Okay. I don't know if anybody here can question the values. I got this from this site, European Biogas. I got this yesterday or yesterday. So before crisis, natural gas was $0.2 per cubic meter. Brazil didn't have a crisis, so I mean it's a constant crisis maybe because the price of natural gas is very high. We didn't have a crisis, but you know the price of natural gas was high. Now with the problem in Europe, the natural gas increased in price and the biomethane stayed the same. At least this is what the site says. Okay. So nobody against these prices. Saying economic aspects. Biomethane is likely to be more expensive for consumers than natural gas. Likely. Okay, so I think when the crisis stops in Europe, maybe the prices will go down. Biomethane prices are expected to decrease due to higher carbon allowance prices. And these carbon allowance prices are going to make a difference. And prices are projected to increase for natural gas, even for cases in which you don't have crisis, okay? Conclusion. Biomethane can be a substitute for natural gas if supply is constant. Supply is constant. Okay, the process is easily convertible from natural gas to biomethane. Biomethane is not a good substitute for coke oven gas in the baking company. There is going to be flame detachment. Combustion equipment has to be redesigned and built. It's very expensive. Supplies don't meet all natural gas demands, at least in Brazil, where 2.2 million, I didn't put the second two in here, or expected by 2027. Okay, when I presented this in AGC, they said, the manager said that this does not supply only the glass companies in Brazil. I don't know how it is in Europe now, but I think that I was doing some work in landfill, for example. You have the 100 to 140 cubic meters per ton of waste. I was going to calculate if this can supply the natural gas in Brazil. Okay, can I finish now? Okay, thank you.
Thanks, João. Very interesting. Do we have any question from the audience?
Was my English too bad?
No, your English was good. I have two questions. The first one to start, and then you keep going, okay? My first question is, how do you explain that the cost, okay, the cost of natural gas can depend from country to country, this we can understand, but the cost of production of biogas, I was expecting it will be less expensive in Brazil than in Europe because you have more space than in Europe to install the plant, and also the labor cost is less, so it's almost double in Brazil. Can you explain why?
Yeah, maybe it is because the technology is starting now. So everything that starts in all countries that you don't have competition, prices go up. But they are selling, you know, this landfill, the Gas Verde Seropédica is selling everything they have just because of the carbon footprint. The companies in Brazil are becoming really interested in fossil fuel.
Okay, and my second question is about, maybe you don't have the answer, but these companies that are actually making some biogas from the waste, you mentioning that they put the waste in the landfill and then they collect the biogas. Do you have an idea how this is done? Because from a practical point of view, if you put something outside, how do you collect the biogas that is produced by the bacteria?
Yeah, I have some idea, but
You visit some of this, no?
yeah, I didn't visit. I just know they get the biogas, but usually you put some covers and you get the biogas.
Okay, so it's covered. So they have the landfill, they cover it.
But let me check on that. I'll tell you that I'm not sure.
Okay. Does someone has an idea?
I was more interested in combustion of it, but
Yeah, but that's interesting that you and several of the speakers today, they were highlighting that we cannot now decouple combustion from the rest. You mentioned several times about the supply chain, the fact that this biogas manufacturer or biomethane manufacturer, they are not able to supply enough. And this is important, that we need to consider the combustion process or the use of the fuel in a complete system, in a complete infrastructure. So this is really important.
one thing that I'm going to ask students to do, to work on knowing the capacity that Brazil has to produce biogas. I know there is a company, an agro-industrial company there in Brazil called Raizen, big one. They work with cane bagasse. They are going to get this biomethane from gasification. But I think it is more difficult to get from gasification because in there you have CO and you don't have a lot of CH4 unless during the gasification you do it with water vapor. Water shift reaction. So let me tell you something. In the beginning of the presentation, I left my email address. I'm just repeating that. I say that the professor repeats everything. Maybe because I'm the oldest in the room. Okay? Marcos, I'm the oldest in the room. Okay? And if you want if anybody of you want the spreadsheet, it's very simple. I made it myself, okay? And it's very useful if you want to mix up to 5 gases. Yes, I don't know if you're gonna give the presentations to this.
So it's up to you. What we have been recording all the videos, so all video will be available online in a few weeks. We need to edit them. We'll send an email to everyone telling that, okay, the video and the photo, they are available. If you want to have a copy of the slides, we ask you to ask directly the speakers, because some of the speakers, they had non-published material. So, but if the speaker, they are okay, they can send it to us, and then you contact us, and we will send the slides that we have.
And I also have, I prepared for today, but it's not on the scope of the presentation. 5 slides showing why certain occasions you cannot use the heat value.
Okay, interesting.
You for the other, okay? That one curve, one enthalpy curve goes to a lower temperature than the other. Okay, so it's it happens in industry. First time I told one of how you call the worker works in the field there, the operator. I told him that the VOB number was important, and he said no. If you give me something with the same VOB number but with lower heat value, then the flame is weak.
Yeah.
Okay, so if you want also, I can give you this 5-slide presentation.
Okay, yeah, please. Thank you very much.
Okay. Thank you.
Any question? No? Okay, so Professor João is here. Don't hesitate to talk to him during the coffee break. Thank you very much.
Thank you.